Good morning, everybody. Today's Code Forces round 2 just started, and here we go. I've got my Code Forces shirt, and this is very important because if you do all this round, you get a Code Forces shirt. So we go minimum sort. In this problem, you need to sort 100 distinct integers in increasing order. You can rearrange the list by swapping the contents of any two positions. They don't need to be adjacent. Unfortunately, you cannot read these two contents directly. You can access the information about the list contents by querying the minimum of a range. It then gives you the position of the minimum value over a range of consecutive positions. Queries about the minimum of the range are limited by the coin budget. Larger ranges are cheaper, asking about the position between the minimum of two positions I and j costs 10 to the 8 divided by their distance coins. Swap operations are free. Write a program that sorts integers. Okay. So we've got some test cases. You can find the minimum, or you can swap two indices. So swap is pretty easy. What if you find the minimum? You get the position of the smallest. Yeah, so we can do 10 to the 8 plus 10 to the 8 over 2 plus 10 to the 8 over 3. Yeah, okay, let's try this just as like a test. Or I equals 2, I is less than Alright, so 10 to the 8 divided by I plus I minus 1. There you go. So that's good enough. So that'll be 4 times 10 to the 8. Good. Be A. And then in temp, we don't need this. In A, we don't need to print it. Okay. So, good. What are we doing here? We can say each essay consists of several exchanges plus an additional line indicating we're done. Alright, T, N. Oh no. Okay, oh, they're all the same. Okay. So, yeah, okay. So then 4 int I equals 1, I plus 1 is less than n plus. Then we want to query the min. The index isn't equal to I. And we need to swap some things. So then we swap mindex, or swap I All right, and then we print done. And we should be good. Okay, so let's try this here. Let's say we have 2 test cases, n equals 3. So the minimum is index 1. That's not right. Test cases, n equals 3, minimum is 1, minimum is 2, then we're done. Okay. Got it. Minimum is 3, swap 1 and 3. Okay. Good. Minimum between these two, let's say this is also 3, swap 2 and 3. Good, and then you're done. Oh, case 2. Never print this. Good. All right, so we should be good there. Let's rename this to solution. And run this. Submit in Java 11. Martyrigons? I think it's like Matryoshka dolls. Yeah, this thing, Matryoshka doll. Matryoshka maybe? Matryoshka. This doll originated in Russia. The defining characteristic is that they consist of a set of dolls that fit nicely inside each other. We want to work with these things, which are regular convex polygons, follow a similar nesting pattern. Matryoshka is that of regular convex polygons, such that for all I, this overlaps with a proper subset of vertices, strictly less than the other. Okay. We've got 2 matrigons. Yeah, first contains 3 vertices. Given a fixed total number of sides, okay. Each of these has 33 total sides in it. Given a fixed total number of sides n, calculate the largest number of polygons that can be part of a matrigon such that the total number of sides in all polygons is exactly n. Yeah, so you please go away. This is literally cancer. This is why no one likes Windows Microsoft. So like dp at x, how many test cases? 100? Like which things can you reach? What's up with this? Okay, we got it. Yeah, this doesn't seem too bad. Let's read the other stuff though. Hidden pancakes. Alright. We cook a pancake with 1 centimeter radius, 2 centimeter, 3 centimeter, and so on, and one with n centimeter radius, not necessarily in that order. Sorry, it's loud. After we cook the first pancake, we just lay it on a plate. After we cook each subsequent pancake, we lay it on top of the previously made pancake, with the centers coinciding such that a pancake is visible from the top when we first add it. It becomes hidden if we later cook one with larger radius. Let this be the number of visible pancakes when it contains exactly I. In the example above, we have these. Given the list, how many of the possible n factorial possible cooking orders yield those values? So it can be really big, print it under mod. So this would be like 1, or this can be anything. Okay, gotcha. This problem doesn't seem too bad. Alright, so initially you just have 1. First number has to be 1. If the second number is 2, then this either needs to go up or down. So if it's 2, the next one needs to be smaller. Okay. Then this one is 2. So it needs to be here. So it's got to be like this. So we've got like this chain. Now we have 3 things, 2 of them are visible. And we have a 1, so the 1 is bigger than everything. Alright. Looks like this is the next most solved one. Let's try this. So you can remove a factor of anything, but you can't end up with a 2, because you can't have a polygon of 2 sides. if we said, okay, so let's say we start with x, then we can hit any like n times x. For any n. Yeah. Oh, I think this might be the same thing. Is it the same thing? Might be. Might be like prime C. Okay. So static int size equals 10 to the 6. Then what? Okay, then 4 int times 2 start times 1 times less than size start plus plus a start times is math max. Oh wait, what am I doing? No, this isn't right. Yeah, because the total number of sides increases in a different way. So if you've got x, it's going to be like the sum of your factors, right? So like it's between x and 2x. That would be the total. Is the total. So it's going to be something like go with the sum of factors and then max size. This one is known. This one we don't care about. not really helpful. Three solves, 136 solves, 2 solves. Seems like the 136 is the way to go. Oh man, but it's so hard. All right, why am I bricking on this? Oh wait, that's it. You just add any multiple of yourself to the total, to total. But you stay at the... Yeah. So what if we had like go at the sum of factors and then the number of steps? It is possible. Oh, duh. Yeah, this is it. So if the number of steps is 1, then it's yes, usually. Otherwise, we brute force what it is. Okay, duh. Let's hurry up with this. Static Boolean possible. How big is n? Do we need to be worried? N to the 6. Okay. Int steps n. dp. dp equals new int array. Yeah, 20 by 21 by 10 to the 6. Alright, so if dp at n steps, the n is not equal to -1, return that. Otherwise, brute force the current size. So if n is equal to 1, return, okay, well I guess if n steps, or if n is less than 3, return dp at n steps, n equals 0. It's not equal to 0. Otherwise, return dp, return true. Otherwise, return false if we can't ever find something to use. Oh man, this is going to be slow, isn't it? Maybe. We'll see. Possibly slow. Okay, so, yeah, we need all of the factors of some number. Can even be a prime factor? Maybe not. Maybe it can't be a prime factor. Yeah, oh, it can be a prime factor. So, static interarray prime fact is new interarray 6 plus 1. Okay. Okay, so prime fact j equals I. All right, so array list integer pfs is a new array list. And for int I in, okay, well, let's just say while on equals n, while on is not equal to 1, and pf equals prime factor of on. Okay. Pf's got add this one while on modulo pf equals 0, on divided by equals this thing, and then we're good. Okay, so for int I in pfs, we can say, if possible, how many steps? N steps minus 1, n minus I, or wait. Oh, darn it. Yeah, okay. We need a can take list. Okay. let's not add this. That's not helpful. Okay. Brute force a factor. Yeah, so now we have all of the possible factors. Okay. So if n plus I is less than lame. Wait, all right. Pause for a minute here. What am I doing? So here are all of the prime factors of me. Yeah. So this is dp at the total, the number of steps, and then current total. Okay, so we need a factor of n minus k. So you take k and then end up with current total minus k. Need a factor of that. Which is also just a factor of us. Yeah, so you can take any factor of us. Is that the case? Let's pause for a moment. All right, so say we need a total of 10 things. We need what we take here. Like, yeah, the total number of sides is 10. So the current number of sides kind of matters. Doesn't matter. Yeah, we just need a factor of us. So this is unhelpful. Yeah, yeah. All right, one more time. Okay, so if mask and 1 to the I not equal to 0, then add times equals pfs dot get I. Should probably be fine. What's our min time limit? 20 seconds? Yeah, okay. All right, good. Finally, so then we can say how many steps? N steps minus 1, n minus I. Wait a minute. So you can subtract any factor. You can subtract a factor. Oh, you subtract the bigger part, and then you keep a factor. So you're left with I. Yeah. That's fine. Okay. Then we return true. And steps. All right, let's make this oh, okay. If I is greater than 2 or less than 3, then continue. No, if it's less than 2, continue. Because you can't take 1. All right. Checking 2, 3. Possible at 1, 3. Oh, yeah. All right, 33. How do you do 33? Is this it? 33? So you do 33, 26, then 6, then 3. Oh. Okay. Let's move on from this problem. That's kind of killing us. Go to hidden pancakes. Ooh, lots of solves. Lots of solves. Okay, hidden pancakes. Yeah, let's pause on B for a moment because it's kind of sucking up all of the time in the world. Come back in a minute. So we've got n pancakes. So we've got this, you can go up or down. Let's, I guess, invert it. Makes it easier. So there's that. We can place something here or here. Doesn't matter. No, because it only matters if it's a new. Wait, okay. So you've got this. We want the longest. Yeah, we want the maximal chain. So if you place something bigger, then this becomes the new bottom. So it's equivalent to like how many top sorts? So we know this is bigger than that. This is bigger than that. We know this is bigger than that. It's bigger than that. So you've got some chain, some decreasing chain, and then you remove several of them. Then you go to this. This is bigger than that. So you have two operations. You have like add to a leaf here, and then you have this thing, like go up K, and then make everything your left child, and then start adding to your right. You have the number of top sorts of a tree. So let's do this real quick. So we have 1, okay, 2, so that means you add it. Then you have 2, so that means this one is between them. Like that. Okay. And then you have a 1, so that means it's here. Like that. It's just one way of doing that. It's explaining the problem statement. It's between them, and then it's the biggest, yeah. Okay. Let's do this one. So 1, and you have a 1. That corresponds to become your parent. So now this is us, and then we have an empty kid, and then plus 1. So we do that. So there are 2 top sorts of this tree. Yeah, okay. Alright, we can do this, I think. is mod 10 to the 9th plus 7, right? Mod 10 to the 9th plus 7. Okay, good. Oh, nice. They have big stuff. Okay. We don't need this. I didn't even notice this sample, to be honest. Okay, so now we have multiple test cases. Good. Int n equals this array, root array size n. A at I is greater than a at I minus 1 plus 1. Then Boolean, well, I guess do this. This is 0, then continue other. Alright, otherwise we have this answer. So then we need long ts ways equals 1. Static void dfs for ts. Okay, then we do node root goes new node. Yeah. Alright, be right back. This is getting really hot. Don't want to lose my cool, you know. All right. So we've got the root. Okay. So we know it's possible. We do meta root.dfs for the top sort. The answer will be meta root.top sort ways. Okay. Alright, so then, oh, we need to DFS for size first. Okay. DFS for size, then DFS for top sort. How big is this? 10 to the 5th? Okay. Long. And then we need fact inverses. All right. Okay. X equals 0, return 1. Otherwise, half equals x base dx over 2. If x mod 2 is equal to 0, return half times half, return half times half times base. Okay, cool. So we have these. Yeah, all right. For node nn in children, nn dot dfs for this. Okay. And then ts ways equals multiply ts ways by nn dot ts ways. Good. Then we need to what else? Yeah, we do that for each kid. This by our total size. So facts at size minus 1. Fact inverses at n dot size. Yeah. I think we should be good. Good there. All right. So now we just need to build this tree. I guess we need the parent too, huh? Prev counter is equal to 0. If I is equal to prev. Okay, so I guess, wait, what is it? So just go up this many. Yeah, okay. So if a at I is equal to prev counter, plus 1. Then node node. New me dot pair equals root. Root dot rightmost equals new me. Root equals new me. Okay. Otherwise, so go up times would be prev counter plus 1 minus 8i. Alright, and then root.children.add root.rightmost. Root.rightmost equals null. And add myself. Okay. So 1, 2, 3. Null pointer exception. Oh. This one. 1, 2, 3. He's got a root node with 2 kids. Oh, yeah, okay. So this isn't children.add. That's not right. Okay, yeah, this is wrong. So yeah, I think we should be fine there. Java, do we need... Okay, before we try this, first of all, this needs to be solution. Come on. Before we run this, let's just make A equal to okay. And then we test. Okay. Read this, and then we'll see. Latest artistic installment is a tiled floor that can be retiled into different patterns. The floor consists of a matrix of R rows and C columns of square tiles. Each tile is reversible, one side's magenta, the other's green. To retile the kitchen, there are 2 allowed operations. Flip a tile, changing its visible color from magenta to green, or vice versa, and swap to adjacent tiles. Okay, we got the first one. Oh wait, ooh. And 3, all right, looks good, looks good. So you can change its thing, or you can swap to adjacent without flipping either. So this might free 2 things at once. Viewing the artistic floor is free, but interacting is not. Performing a single tile flip costs F, Performing a single swap costs S. You can see the current state of the floor and want to turn it into a particular pattern. What's the minimum amount of coins you need to spend to achieve your goal? Flow. Alright, I have to go to the bathroom. But I'll think about this and consider matrigons as well. Maybe we should look at the scoreboard here. So lots of people have this, lots of people have that, so we need at least one more for sure. If we got, this is more points, so if we got this, that would be epic. Can I view my friends? Yeah, looks like this isn't that bad. Okay. Right. So upon having a brain, I think I've realized this is the easiest problem in the set. If I'm understanding it correctly, here's the reasoning of why. Where's my pen? You're never going to swap, if these are both red, you would never swap these twice, right? Like, you only swap two things if, ooh, wait a minute. If we have a green here, and then a red, and then a red. Wait, what do we need to do? We need to convert it from this into this. 2x4, yeah. Convert one into the other. So, oh, I see. So you can do this. How big is the board? Each of them cost 1. Oh, it's up to 10 by 10. Okay. Well, we can get the 11-point part for sure. I think. have a pink and a green. We have a 0 and a 1. Like, you're never going to swap two zeros. You're never going to swap two ones, so you might as well just not do the swap. So you're always going to have like a 0 and a 1 next to each other that you swap. The concern is you might do something like this, where you have a 0 next to a 0 next to a 1, and you might do two swaps here. But you would never, along this path, want to do something like this. Would you? Yeah, you never want like paths to overlap. You'd always just, if you had something like this, you'd never try and match these two and these two, because you could just do this, and that's equivalent. So I think it's just the minimal matching. So you've got like the pinks and the greens, and then the source, and then the sink. Each of these can match at most once. So each of these have a cost of 1. Each of these have a cost of 1. You want the minimum cost to match each of them. But oh, that's not the case. Because you have pink starts, pink ends, green starts, green ends. Okay. Well, okay, if it stays the same, then you might as well just leave it. There's no use in keeping it, so then you ignore. Yeah, just never touch something that stays the same. Yeah, okay. Otherwise, you have a 0 to a 1, that's one type, and then a 1 to a 0. So let's call these like pinks, I guess. And let's call these greens. So you have pink here and then green here. And then you want to match them. You have the cost of matching them. But you can also skip a matching for like two flips. Yeah, okay. I think that's it. And that's just regular flow. You want the minimum cost of doing it. No. We want min cost max flow. Because each of these are 1. 1 and 1. Yeah. Oh, you can also... Okay, I think we can get this problem by the end of contest, but so you need to match all of these things. Oh, you can also match this to like none if you want. You can match this to none. Yeah, okay. All right. Let's get our min cost max flow here. Source, graphs, flow, min cost max flow 4. All right, yeah. We have height, width, then cost 1, cost 2. Okay, so then we want point array, I guess array list, point p1s, x equals 0, less than height, x plus, y equals 0, y is less than width, 0, y is less than width, x plus. There's some cases here, so if board 1 at xy equals board 2 at xy, then continue. Don't bother, yep. If board 1 xy equals m, then p1s dot add new point xy, else p2s dot add xy. All right, so now we need our min cost max flow thing. All right, so let's do this graph here. So we've got the pinks, we've got the greens. Each of these need to be matched once. Okay, then we have the edges between them with the costs. And then we have the edges to this, we've got like skip. So this has like infinity, this has infinity. Alright, so we want to take each of these. So make each of these very negative. And then these cause 0. And these are bad. So make them positive. And then we know these costs 2. Okay. So we have P1s, P2s, skip left, skip R, MC, MF. P1's dot size plus P2's dot size plus 1 plus 1. Oh wait, how big can these things get? 10 to the 6. 1, 2, 3. Hope this isn't going to be an issue. Oh man, I gotta figure this out. So this first thing is the flow. Yeah. So inf1 is just the max flow. Yeah, inf1 is the max flow. Inf1 is the max flow. Do we need this? This is never used, okay. Should there be negative cycles? Probably not. I don't think there are any cycles even. Yeah, no cycles, okay. Okay, inf1. What is this? Do we need this? Oh, it's only 10 by 10. Yeah. Okay, good. This can be smaller. This can be like 5 times 10 to the 7 even. 50, yeah, that should be fine. Okay. Ah, good. Infinities all work out, right? 10 to the 8, 10 to the 9. Good, okay. Amazing. Okay. Plus equals free amount times. We get 1 for each thing. So P1's dot size plus P2's dot size. This can be a long, I guess. Sure. Okay, that should be fine. Okay. min cost is this. Yep. Plus min cost. Okay, now we just need to build our graph. Yeah. Yep. I equals 0 less than p1's dot size plus j equals 0, j is less than p2's dot size, j plus. This, okay, point p1, p1's I get I, p2 plus p2's I get j, dist math.abs, p1.x minus p2.x plus math.abs p1.y minus p2.y. Go from I to p1's dot size. Thought I was going to sneeze, never mind. Plus j. The cap is 1. The cost is the distance. Okay. I equals 0 less than p1's dot size plus p2's dot size. Oh, yeah. Plus mcf dot add. Go from mcf dot source to I. The capacity is 1. The cost is -3 amount. Yep, okay. This times cost 1 or cost 2? Swapping, so cost 2. Cost flip. All right. Yeah, we have each of those. Okay, so this is the source. Then we need the sink. So we need p1's dot size plus 1 or plus I. P2's dot size to mcf dot t. 1 -3 amount. Yep, because we want it. Good. And then we need to do these both one more time. So we go from I to p1's dot size plus p2's dot size plus 1. Cap is 1. The amount is cost of a flip. Okay. And then we go from this thing to this. This is also cost flip. All right, so we add those edges, these are the skip edges, and then we add all the normal edges. And we run this, and we get the problem right? What? Oh, no. Yeah, cost flip. Okay. times 1 by 1, and we get m to g should cost 1. One test case. Is this equal to free amount by chance? I think it is. Oh yeah, we need the edges from these free things. So mcf.add p1's dot size plus p2's dot size plus 1 to mcf dot sync capacity p1's dot size plus p2's dot size plus 1. Oh yeah, cost is 0. We go from source to this p1's dot size, p2's dot size, same thing. Okay. Three to 0 to 2 to 4. Should be a path here. 3 to 0, 0 to 2, 2 to 4. What the heck? Shouldn't be any negative cycles. Yeah, I shouldn't need this. What the heck? What the heck? What am I doing with my life? What? It's been the same since as we've had this for over a year. Source to 0. And you've got 1, 2, sink. Cap 1, 1, negative dk. One to 2, or 0 to 2, $1, $1, 2 to 4, $1, $0. Is this 50K too big? Is that the problem? Okay, well, we're just not going to use this method then, because it might be broken. Alright, what's here? We don't need this. Flow and cost. Okay, I don't know what the heck that was. Okay, finally. Five, six. Oh boy. Oh boy. M, G, M, G, M, 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 G. 2, G, M, G, M, 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 M. So these three stay the same, otherwise they change. So you've got 0, 1, 0, 1, 1. Zero, 1, 2, 3, 4, This will be 5. Oh, then we have 5, 6, 7. Oh, we also need this edge here. Yeah, okay, so then... Three, 4. Okay. Three, 4. 1003. Let's modify this a little bit. Just 2. 1006 probably. Yeah, okay. And then we change these. Oh wait, do we have another? This was this one before. Yeah, okay. So then if we make each of these 2, 2, then it should be 6, 8. 6, 8. Looks good. Let's submit. Java 11. Okay. Looks like we got first one. Okay, not great at all. So we might need this one depending on things. Does this have, what are the 2 bounds? These are each 1. I don't know. Okay. There might be some fake solves on this, possibly. I don't know. So let's get this. Okay. So we have, well, in a bit. Pro strats, half an hour left. Not quite, less than half an hour left. How do we do this problem? So, small lets you do the n squared, right? 20 seconds. Uh-oh. Maybe you could just pre-comp all of the answers. So you do a DP where you store the sum and, yeah, total number. Okay. That's one option. So I think we have that. So I think this is the last problem left. So we just have DP at sum and then cur size. This is the naive. And then we can say take any factor of cur size, and then you go to sum, or okay, so sum minus like n minus k. sum minus cur size, and then that's the feature sum. The feature size is the factor. You could also do dp at sum and then cur size, and then you could say add any multiple, and then you go to dp at sum plus like multiple, and then the new multiple. Yeah, I guess that's a thing. Or I guess this is B2 actually. Okay, so static long to L into A, B, turn A times long 1E9 plus B. So cool. we're doing the start size. Do I just want to implement this, or do I want to think of the right solution? I might not be getting B large, because this is going to be slow. So this is going to be size, or total, and then cur size. Or do we want it the other way around? Probably cur size total. Yeah. Oh, we don't need factors of, actually. We don't need this, we don't need this. Okay, trial multiples. 0, and then from dfs.add. No. Okay. All right. So if I make this bigger, yeah. Just passes the small but not the big. I don't know how to do the big. Because I'm a dum-dum. Man, I'm really crossing my fingers for these. Yeah, like all my friends have this. Oh my goodness. I'm not seeing it. Oh, maybe you could start with one thing and then like divide it up. So you multiply it by some constant. Yeah, so you have some constant at the end. So you can the total number of sides, yeah. So you can multiply this by any constant at the end. So then you can say, you can add any number. Oh, so you subtract 1. Then you can add any number and then divide by that. This is easy. Yeah. Okay. Oh, what am I doing? Yeah. So you start with 1, and you can hit yes, you can add 2 or more, and then multiply that by some constant. So some factor of 2 or more times 1. This is any multiple of 2. You can add any multiple of 2 or any multiple of 3 or any multiple of 4 or any multiple of 5, 6. And you need some factor of yourself. Man, I'm just barely out of time. You do an n log squared, probably a bit faster. All right, well, let's see. See how we did. Oh, top 1,000. Okay. I just need top 1,000, so I think I should be fine, probably. If I get one of these, yeah, I need to get one of them. At least. Then I'll advance. This is a little nerve-wracking. I'm cutting it way too close to the wire. Alright, so I got both of them. 280. Not bad, not bad. Yeah. Looks like not solving set was a problem. So I lost to most of my friends. Yeah. Not bad, not bad. I think I got a t-shirt, which is what counts. So it was a tough round. Tough round. I guess it wasn't that bad. I was just being a brick. A little bit of a brick. But that's fine. I'm glad I didn't sink the entire contest on B. Could have been a lot worse. I could have not qualified. But yeah, I thought the problems are pretty good. I guess I'll talk about them real quick, and then I have another thing I have to do coming up, another contest. Ugh. So here we go, minimum sort. Yeah, so the observation here is that the harmonic sum is n log n. So if you look at n plus n over 2 plus n over 3 plus n over 4 plus n over 5 plus n over 6, that will be, it sums up to like n log n. So if you add up each of those numbers, 10 to the 8 over 2 plus 10 to the 8 over 3 plus 10 to the 8 over 4, all the way up, then you'll get a total of about 4.5 times 10 to the 8, which is underneath this max cost. So basically you have to make sure that you only query like a range of each size once. You do that pretty easily by querying the entire range, finding the smallest thing, and then moving that to the front. You just keep doing that, eventually it'll be sorted. And that will take exactly this many moves. So that's it. That's minimum sort. Should be pretty easy. This one, yikes, I don't know. You can do an n squared dp if you're just looking for how to do it naively, and that will get you the small test set. The big test set I have some ideas for, but not a working solution. So yeah, there are lots of people who can help you with that. Apparently I can't. So if you want to beat me, there you go. Solve this hard problem. I'm sure analysis test set 2, here you go. What's this dp? Okay, yeah, I don't know. I don't have time to read this on camera, but I will later. Hidden pancakes, what is this one? Oh yeah, so this is a cool problem. So it's pretty intuitive, right? You've got these pictures. Let's see the problem here. Yeah, so like when you put a pancake on top, it hides the smaller ones. So the question is, if you're given the order of these, how many different relative sizes can there be? So here you have one pancake visible, two visible, two visible, one visible. So how many, like, of the n factorial orderings, how many different ones are possible, which would give you this ordering? So the key thing here is you can make a dependency graph of which pancakes need to be bigger than which other ones. And if you look at the minimal version of that graph, it turns out you'll have a tree. Because it's like the maximum, well, I don't know. It's like you can define that graph of like, you have an edge from A to B if A has to be bigger than B. You can define that graph as a tree because of how you build it. So let me talk about how you do that real quick. Basically, initially you have just one pancake. If your next pancake is bigger or is smaller, then you have to be smaller than it. So now you have 2 visible. If your next one is smaller, then you'll have 3 visible, right? And then maybe after that you have 4 visible. But then after this, you only have 2 pancakes visible. So that means this one got covered, this one got covered, and this one also got covered. So the one you're adding has to be here, has to be bigger than each of these 3, so you add this edge here, but it has to be smaller than this because it didn't cover that, and now you no longer need this edge. Right? And now if we add another pancake that's smaller than this, right, now we'll have 3 visible, 4 visible, 5 visible, and then maybe we cover this one up, so we add this edge here, add this, add that, we add this here, and then remove this edge. So it looks like this. And then in the future, we'll keep adding here. So you make a tree. That's what I'm saying. Once you have this tree, the tree is the list of all of the requirements that you have. So any top sort of the tree is a valid solution, and you need to count how many top sorts there are of this tree. That's a pretty common problem. To do that, you look at it from some node's perspective. So you have all of the nodes in this subtree and all of the nodes in this subtree. You have to do each of those subtrees. So like the DP for this node is the product of the DP for the 2 subtrees, but also you don't have to do the entire left one before you do the entire right one. You can alternate them. So you've got like multi-choose, right? So this has 1, 2, 3, 4, 5, 6, 7, 8 grandchildren, or like 8 descendants. So it's 8 factorial over this size thing. So this is 3 factorial. This one is 1, 2, 3, 4 over 5 factorial. And if you had a third group of like 1 here, right, then it would be 9 over 3 factorial, 5 factorial, 1 factorial. Yeah. So this is multi-choose, so this is the number of ways of interleaving these elements. Cool, so there's that. And then one more problem here. We've got retiling. So this one was a bit messy, but it just screams some sort of flow solution. Find the minimum way of doing this, and there are like 2 different things you can do, and one of them is a fixed cost, and then you got the other stuff. So you can do it with minimum cost flow. Looks like my minimum cost flow code was broken, so I had to fix mine in contest, which was a problem, maybe part of the reason I didn't get B. So there's something for me to do. There's some homework for me. But yeah, so the idea is that you're never going to flip 2 tiles next to each other that have the same value. The only time you do this is if they have a different value. And then the next idea is I'm going to just throw out here, if you have a 1 and a 0, you can always just flip these in a continuous range. And then the cost of doing that will just be the cost along this path. Well, you might say, but David, what if you have like, you know, a 0 here and then a 1 here, right? And then you can combine these 2 for free by doing this. So they're not independent. But my response to that would be, well, yes, they are, because instead of combining these ones and then getting this for free, you could instead just combine these 2 and these 2. So it still works. Yeah, so that's the idea there. So that's kind of the general solution for that. So then where we are now is you've got a bunch of ones and a bunch of zeros, and you want to match them up. I guess for ones and zeros, let me further dig down on that a little bit more. If you have a 1, if you have like a G and it stays a G forever, then you're never gonna, like, don't worry about it. Just ignore it, keep it the same. You can have something pass over it, but if you have like an R or an M here, and you swap with this G, and then you have an M over here, and then you've got a G over here, I guess. So you move the M all the way across this G, this will stay a G. So basically you can ignore it if it stays between the beginning and the end. If it stays the same, just ignore it. Same thing if it's an M. So now we have two types of tiles. I call them 0 and 1. The 0 tiles go from an M to a G, and then the 1 tiles go from a G to an M. And if you match a 1 and a 0 tile, that's the same as saying, okay, these two are going to swap. And that will give us what we want. So you want to find the minimum cost matching, where there are two things you can do. You can either swap a 1, or you can like match a 1 and a 0, and you can only match each tile once. Or you can like turn a 0 into a 1. So those are the two types of costs. And then to match a 0 and a 1, each one has like a different cost, which is their distance on the plane, their Manhattan distance. Okay, so what now? We had, how do we handle this fact that like it's not quite minimum cost matching? It's like kind of minimum cost bipartite matching, but not quite. The way we can handle that is, so we've got a bunch of zeros on one side over here. So these are all the zeros. These are all the ones. And then we have a bunch of edges between these, saying you can match this 0 with this 1, this 0 with this 1, it costs this. Each of these things you have to match once. And each of these you have to match once. So these are the capacities of these edges on the flow graph. And then I also create these two free nodes. So these are like skip nodes. So you're allowed to skip. You can like skip a 0 or skip a 1. And then if you skip a 0, the cost of doing that is just the skip cost. If you skip a 1, you have some other cost of doing it. So yeah, that's the idea behind the solution. So for some pair, you can either skip it or you can match it, and then you just have to handle the capacities. So these have infinite capacity, 0 cost. All of these have 1 capacity, 0 cost. Or these have negative infinity cost, sorry. Because you really want to take them. Like you want to match all of these things. 1 capacity, negative infinity cost. And then each of these have 1 capacity and then like some constant cost, where this constant is like the distance between them. That's the cost. So when you run min cost max flow, you'll have a flow of 1 going through each of these because of this negative infinity, and then also a flow of 1 coming out of each of these, which means everything will be matched or skipped. And then at the end, since we have 6 zeros and 6 ones in this case, we add 6 times infinity to our answer, because we'll have subtracted infinity 6 times because we want the minimum, so we add them back in to get like a normal number. All right, that's the solution to that. So I've got solutions to all the problems but B. And yeah, looks good. So looks like I made it on 285th place, so not good. It's pretty not good. How many people solved set? A lot. If I'm gonna make the finals, I need to be solving set. For this case, at least. Oh, okay. So looks like I did best. Of the people who didn't solve set, I did best. Yeah, so live and learn, next time solve set, right? Okay, yeah, that's all from me. Hopefully you enjoyed the set, and hopefully you won a t-shirt, because that's, you know, life goal. That's what you look forward to in life. I don't know if I want a t-shirt, actually. I'll have to check. It might be top 200. It might be top 1,000. I'm not really sure. But yeah. Okay, thanks for watching. Have a great day, and see you in round 3. Goodbye.